Good morning. Today we discuss about crystal systems. According to the geometrical consideration, that is symmetry and internal structure, the crystal structures can be classified into 32 classes. But we can group them into 7 according to the lattice parameters. We know that A, B, C and alpha, beta, gamma. A unit cell can be represented by using the lattice parameters. So the 7 basic crystal system are distinguished from one another by the angles between 3 axes and the intercepts of faces along them. That is, we can classify the crystal systems based on A, B, C and alpha, beta, gamma, the values of sides and angles. So the classifications are cubic, tetragonal, orthorhombic, monoclinic, triclinic, trigonal or rhombohedral, and the last is hexagonal. And look at the classifications. Cubic unit cell, tetragonal unit cell, orthorhombic unit cell, rhombohedral unit cell, monoclinic unit cell, hexagonal unit cell, and triclinic unit cell. Now look at their values. In cubic unit cell, the axial distance are equal and the angles are equal and it is equal to 90 degree. In tetragonal, A is equal to B, not equal to C, and the angles are equal and it is 90 degree. In orthorhombic, the axial distance are different. A not equal to B, not equal to C, and the angles are same and it is equal to 90 degree. Just look at the shape of the different crystal systems. This is cubic unit cell, tetragonal unit cell, orthorhombic unit cell, rhombohedral unit cell, monoclinic unit cell, hexagonal unit cell, and triconic unit cell. Here the parameters representing different systems. In cubic, A equal to B equal to C, and alpha is equal to beta is equal to gamma is equal to 90 degree. In the rhombohedral, A is equal to B equal to C, and angles are equal but not equal to 90 degree. Look at the shape. In hexagonal, A is equal to B not equal to C, alpha equal to beta is equal to 90 degree, and gamma is equal to 120 degree. In tetragonal, A is equal to B, that is not equal to C, and the angles are equal and it is 90 degree. In orthorhombic, the sides are not equals. A not equal to B, not equal to C, but the angles are equal and it is equal to 90 degree. In monoclinic, sides are not equal and alpha equal to gamma equal to 90 degree, beta not equal to 90 degree. In triclinic, the sides are not equal and the angles are not equal and not equal to 90 degree. And the details and some examples. For the cubic structure, sodium chloride and for tetragonal example is SnO2, and for orthorhombic KNO3, and for monoclinic Na2SO4, and triclinic CuSO4, and trigonal CaSO4, and for hexagonal SiO2. You should familiar with the 7 crystal systems and the details about the lattice parameters, that is the values of alpha, beta and gamma, and A and B and C. And next is the crystal symmetry. What do you mean by symmetry? In crystals, if a definite ordered arrangement of faces and edges of a crystal is found, it is the crystal symmetry. By crystal symmetry, we means the definite ordered arrangement of faces and edges of a crystal. Crystal possess different symmetries and symmetries elements. They are described by some certain operations. A symmetry operation is the one that leaves the crystal and its environment invariant. If we are performing some rotations or reflections or some translation, and in any operation, if the crystal and its environment is invariant, then that particular operation must be a symmetric operation. And the symmetry operation performed by a point or about a line is called point group symmetry operation, and the symmetry operation performed by translation as well as rotation are called space group symmetry operations. So there are two types of symmetry operations: point group symmetry operations and space group symmetry operations. In point group symmetry operations, the symmetry operation performed about a point or a line, and in space group symmetry operations, the symmetry operation is performed by translation as well as rotation. Now we discuss more about the point group symmetry elements. First is center of symmetry or inversion center, reflection symmetry, and rotation symmetry. The center of symmetry or inversion center. To discuss about symmetries, we take a cube. We know that a cube possesses three pairs of parallel and opposite faces. Here in the figure, the shaded faces is one example. Similarly, there is two other such pairs. In a cube, all of them same size and shape. Hence, a cube is said to show a center of symmetry. It must be the body center of the cube. It is called a center of symmetry. If we draw two body diagonals, it will intercept at the center. Okay, or it is the center of symmetry. This center lies at equal distance from the various symmetrical positions. The center must be at equal distance from the three pairs of faces. The center of symmetry, also known as inversion center, because of from that point, from that center, we can view that all the faces are at equal distances, or from at that point the cube possesses symmetric shape. Okay, next is plane of symmetry. A crystal is said to possess reflection symmetry about a plane. if it is left unchanged, if it is invariant in every respect after being reflected by the plane. If we perform any operation, if the after the operation, if it is invariant, we will take it as symmetric operation. Okay. A highly regular crystal may be bilaterally symmetrical about several planes, cutting them in different directions. They may have several planes of symmetry. However, a plane of symmetry is different from a plane of geometrical symmetry, in that a plane of symmetry cut the crystal into two halves such that one is the mirror image of the other, or it is one is identical to other in all respects. A cube has three straight planes of symmetry and six diagonal planes of symmetry. First we see the straight planes. These are the three straight planes symmetry. When we divide the cube through that planes, it will give you two identical divisions. So a cube has three straight planes of symmetry. One is in X, and one parallel to Y and one parallel to Z. And there are six diagonal planes of symmetry. Look at the planes. There are six such planes. So a cube has six diagonal planes of symmetry. If we cut the crystal in such a plane, we will get two identical pieces. These are the planes of symmetry. Here the first three is straight plane symmetry and the other six are diagonal planes of symmetry. So there are totally 9 planes of symmetry. Then the axis of symmetry. A body is said to possess rotational symmetry about an axis if, after the rotation of the body about this axis by some angle theta, the body appears as it did prior to rotation, or the body is left invariant as a result of rotation. This axis of symmetry may thus be defined to be a line such that crystal assumes a congruent position for every rotation of 360 by n degree. A cube is rotated about a line perpendicular to one of its faces. As its midpoint, it will turn into a congruent position in every 90 degree. Four times during a complete revolution. So we called it has a fourfold symmetry, and the axis is called tetrad axis. A cube clearly possesses three such axes. One normal to each of three pairs of parallel faces. So this cube, the axis passes through the center of faces, each pair of faces. Okay, so there are three such axes. It is called tetrad axis. Next is if it is rotated about a solid diagonal. Solid diagonal means it is an axis from one corner to the diagonally opposite corner. It is a body diagonal, and it is rotated 120 degree about the solid diagonal or the body diagonal. So this axis is known as triad axis, and it has a order of 3. By an order of 3 means if we perform 3 such operations, it will reach at the initial position. It is this axis. And the next is Diode axis. It is the line joining the midpoints of pair of opposite parallel edges. Diagonally, it is the midpoints of the diagonally opposite parallel edges. Through that axis, if we perform a rotation of 180 degree twice, it will come to the initial position. So for a diode axis, the order is 2. In a cube, there must be such 6 axes. So there are 3 tetrad axes and 4 triad axis and 6 diode axis. The operations will be clear in this video. First is the tetrad axis. Through this phase, the axis is going to the opposite phase. And here we rotate about 90 degree. It is a rotation axis, and if we rotated 90 degree, the shape is not changed. It is the third one. And if we one more rotation, it becomes the initial position. So it has order of 4. Okay. If you rotate a 90 degree, as it is symmetric, it is gives the same shape. Okay. And we perform another rotation 90, then it also gives the same shape, and the next 90 it gives the same shape, and by the 4th rotation it will reaches the initial position. So we called it has a tetrad axis and it has order of 4. And the next is triad axis. In this case, the axis passing through solid diagonal. It is the solid diagonal or body diagonal from one corner to diagonally opposite other corner. This is the rotational axis, and here we mark the shape as this, rotated by a 120 degree. The shape, the shape, the same shape comes, and another 120 shape is also correct, and by the third rotation it will give the initial position. So we call it has order 3, and it is a triad axis. And the next is diode axis. It is the diode axis is passing through the midpoints of diagonally opposite edges. Here this edge, and it passing through the opposite diagonal edge, and now we can mark the shape. And here we rotate it by 180 degree. The shape retains, and make another 180. It reaches the initial, so the order is 2. It is diode axis. So there are 23 symmetric elements in a cubical system that we discussed are: first we discuss the center of symmetry, only one center of symmetry, one point of symmetry, and the planes of symmetry in straight planes 3 and diagonal planes 6. There are 9 planes of symmetry, and 3 tetrad axis, 4 triad axis, 6 diode axis. So 13 axis of symmetry. So when we sum it, we will get total 23 symmetric elements. So I stop here. We will continue with the combinations of symmetry elements in the next session.